I lead up the threat intel team at Velexity. Today's story, if you like, comes from the incident response practice, really. But we're a relatively small firm. So when there are IR gigs, I'm often able to contribute. And that was the case in both of the cases that we'll be discussing today. So I've gone with a semi-punny title. It's been 0 days since our last incident sign in the factory. In this case, we're talking about not incidents in a physical factory, but on edge devices. That is a kind of a growing trend, but we'll get into that in the coming slides. What are we talking about? Edge devices is actually a very ill-defined term. If you were to go on like Google and get people to read up on what edge devices are, there's like varying definitions, all of which are like Venn diagrams of different categories of device. But for the purposes of this talk, we are actually only talking about a very small subset of edge devices. And ironically, those are not like file transfer servers. They're actually security products that are intended to prevent intruders from coming into networks. And those products are subject to vulnerabilities. And those vulnerabilities actually facilitated access to those networks. So like the very last thing that the designers of these products wanted them to do has happened. And so the talk really focuses on two things. The first is, what do these attacks look like? So effectively, I'll take you through how we discovered them, the different things the attackers did during those attacks. And although both of the cases really involve the root cause is a zero-day vulnerability, it could have been any vulnerability or any intrusion. Really, the same types of things happen. And so it's just like a kind of view into what IR looks like. And then towards the end, there's kind of some general musing about the types of things you could do to identify or stop similar attacks on your network. So our first case is Ivanti Connect Secure. So like all of the best stories I know, it begins with an alert. So this alert was actually the same alert. I believe it's the exact same signature that was used for our 2021 discovery on Exchange, which looks for web shells on Exchange servers. That's like the whole idea of the rule. And the premise of the logic of the rule is that Exchange servers are relatively static. Not a lot changes on the Exchange server. And when an attacker adds a web shell, they are changing the set of files that exists, and that is a very rare event. And so we got this alert, and we thought, hey, there's going to be a new Exchange vulnerability. We are going to be very popular. And the first thing you do when you get an alert is you go and say, hey, is this a true positive or a false positive? So sometimes you could write the best signatures in the world, but if you've done any kind of network monitoring, you'll know that it doesn't matter how good your signatures are. Eventually, you are going to write some that produce false positives. But that's not the case in this case. We go and grab the file, and just reading like the first 10 lines of the code, we're just like, oh, it's reading a obscure request header. It's like reading out the contents of that into like a binary object, and then it's very difficult to show like full web shells or like any kind of malware in a slide. But effectively, there's another 70 lines beneath this, and there's this case statement that says if the code has this in it, then like execute a command. If it has this in it, go and download a file from the URL in the next parameter. It is a classic web shell. And so we're very lucky with a lot of customers, and for this customer as well, in that we're very quickly able to do investigations. So within kind of hours of the first alert, we are quickly gathering memory and key files from the web server, in this case Exchange. And when we go and like analyze all the evidence, it quickly comes down to the fact that, hey, this isn't a vulnerability in Exchange. That's not where the problem began. The problem began elsewhere on the network, because the first attacker activity is 6 days prior to our alert, and it's an admin login from another IP. And when we go and check what that IP is, turns out is the Ivanti device. And so the next logical step, like all of the IRs generally follow this pattern in that we're trying to get to the earliest activity, find out how the attacker got in, and then you can start to think about how you might remove them from the network. So all the roads that we kind of look down lead not to Rome, but to the ICS VPN device. And so we have a range of customers that we do network security monitoring for, and like there will be times when we'll do this and we'll get to the device and we'll find out that it hasn't been patched in 18 months. So we go in with that kind of expectation that, hey, maybe we're just going to find out there's some unpatched system somewhere. But actually what we do find is that's not the case. It's completely up to date. And so the next thing you want to do in an IR generally is get logs. and we go to try and get logs, but it seems like the logging interface is like broken. So you go to the user interface where you're meant to download logs from the web panel, and they're just not there, which is strange. And a lot of this activity and what I'm describing in these slides is all happening concurrently. There's no way to like organize it in a way that kind of shows that. But another thing we do is look at network connections. So we've got the sensors, which often, as Stephen described in the keynote, can see both inside and outside the network and laterally. And we know the IP of the VPN device, so we think, hey, we'll just go and take a look at all the network connections that are going on. And what you generally find with this class of device is that once you filter out certain types of connection, there's not a lot remaining because the pattern of life for the device is generally quite static. So once you filter out that, you end up with a set of activity that is effectively everything that's happening in the intrusion. So one of the like very big red flag items is the outbound curl request to ipapi.com, a website that allows you to retrieve the current IP of the machine you're on. And that type of thing is something that is very common for an attacker to do as their first or second command on a box. It's a way of doing two things. You verify that you've got outbound internet connectivity. Maybe there's like firewall or proxy issues you might encounter that you need to check. And you can also verify like that you are on the box you think you are. There's a lot of outbound activity to cyber-owned devices. So the attackers in this case, it's not covered in this presentation. But the attackers use this network of compromised devices in order to interact with the malware that they installed. And crucially, we see a lot of inbound RDP and SMB to other machines on the network, some of which we already know are compromised from other investigation streams. And the kind of cherry on the cake is that when you use RDP or SMB, the computer name is embedded in the protocol, the computer name that you're connecting from, and it shows a non-standard computer name. So in the case that the affected organization was like Velexity, they would organize all their computers as like vol1, vol2, vol3. That's how they name every host name. But in this case, the host name is like desktop 1AB48B, which is like the attacker's machine name. So we're getting quite suspicious. And another kind of thing that we often find in these cases is that some of our customers are subject to a lot of attacks on these types of devices. And there'll be like a very near kind of end day. And so we go on the Ivanti website on like December 12th, 13th. And on December 10th or so, a couple of days prior, there's a new remote code execution vulnerability, which I'm sure Ivanti are sick of putting on their security page by now. But there are a couple of things that mean it can't be that vulnerability that's responsible for our intrusion. The first is that it was discovered by a French red teaming company called Synactive, and they don't talk about it being used in the wild. And that's not like a kind of silver bullet as to why it can't be that vulnerability. The silver bullet is that it affects the admin panel. So there's two components to the device, the admin and the user. And the admin panel is only accessible if you're already on the network in this case. So can't be that. So we think, hey, there's probably a 0-day in play. Ivanti offers this tool. This is actually a common type of tool that these edge device vendors will kind of ship with, called the Integrity Checker tool. And there are two versions of the tool, the built-in one and the external one. The built-in one runs on the box. The external one requires a reboot and runs from off box. And the built-in one, you like access it through the admin panel, and you click run. And when that happened, circle just spins, doesn't ever complete, which is, again, suspicious. But the external one, when you run it, showed a number of mismatched files. So effectively, the Integrity Check tool's job is to say, are the files on the device the files that are meant to be on the device? And if they are not, then why not? And so the workflow that Ivanti expects customers to take with this is that you are meant to send these files to Ivanti, and they will decrypt them for you. However, as they have found out, that is not a sustainable model when there are lots of customers who are trying to ask you to do that. And also, if you have some smart people, so some of the software team, we're able to reverse engineer how that works, and we decrypted the results ourselves. So a review of these decrypted results shows various things that kind of support what you might expect. So various bash scripts designed to install things, like make sure that their web shells are working. The edits to the ICT exclusion list, which is why the Integrity Checker tool did not work. So they tried to modify the exclusion list, which is used to configure the integrity checker tool to tell it which files are expected to change, and the attacker was adding every file that they had modified to that list, but they had made a typo, which was causing the bit that reads that list in to fail. One of the kind of hallmarks of what I would say are the better attackers attacking these types of device is that rather than adding new files necessarily for their web shell component, they would modify existing ones, which means that when you're analyzing the logs of like inbound requests to the device, you have to sort out the like actual requests to that API endpoint or whatever it might be from just attacker requests, which is what would happen if the file was just owned by the attacker. And all they added was really these 8 lines, but they were amongst like a 600-line Perl script, which made it much harder to find. So we've done all these things, many of them in parallel, and we're now pretty confident that the device is compromised. Like, hey, it's time to do some forensics. But one of the general problems with doing forensics, or any investigation, in fact, on this class of device, is that you can't just SSH in and run Velexity search. Oh no, you have to call them up and explain that you think your device is compromised. Jump on a video call, at which point they will get a shell on the box, and you have to tell them line by line what to type. And so that's what Stephen and Sean had to do over a course of, I think, like weeks. Because you've got to convince them that you were the real deal. You've got to. They get lots of cases of people who think their like device is compromised, and they're used to people like getting it wrong effectively. But eventually, we did get a forensic collection, and because we'd had lots of other streams of investigation, we had a huge number of IOCs. We had like all the cyber MIPs we know about from the network traffic. We have the results from the integrity checker, and we find a great deal of information about what the attackers have been doing on the device. But crucially, what we don't find is any vulnerability, because too much time has passed since the actual exploitation and the time this happened. So it's something like 2 weeks, which means there's nothing in memory, because memory is good, but not that good. And there's nothing in the logs, because the attackers are smart and have deleted them. And so our only real recourse is to tell the customer, we're going to clean up, set you back up the way you were, and see what happens. So it's not ideal for the customer, because we are fairly confident that an attacker somewhere on the internet is going to run a magic command and then be on their device. But we continue to watch the network, and we basically set traps so that when the attacker comes back, we're going to know about it. And then it was the night after Christmas, and all was not still. So there was a new alert, effectively, that we'd written dedicated for this device to look for outbound SSH. So SSH from the device to other machines internally on the network, which never happens. And then, hey presto, we think we're off to the races. So we run the internal integrity checker tool, which is an important distinction, because previously we had to run the external one, which reboots the device, which is bad for analysis. But this time, we run the internal one, and we do get a mismatched hit. So effectively, the attackers had replayed the same vulnerability they did before and had returned. But this time, things didn't go so well for them, because we had the contact set of Avanti that we'd forged kind of the previous couple of weeks. And so within kind of the day, we were able to get them on the phone, collect memory and disk, and crucially, it's kind of before any time has passed for the attacker to delete evidence, and also before the device was rebooted. I always feel silly doing this bit, because it's like very easy in some ways. But one of the things we find like again and again with this class of vulnerability is it's often the case with these vulnerabilities that are on edge devices that they are command injection vulns. So there's some parameter sanitization problem that the attacker has found, where a variable in a request is going to get passed to the shell, and they just need to manipulate that. And if you're trying to exploit that class of vulnerability, one kind of problem for you is that you need your command to run in exactly the way you intended it to, and URL encoding is a problem. So what they frequently do is wrap their whole thing in base64, and they have to worry less about encoding issues. And so looking for base64-D is a very good starting point. And lo and behold, just within kind of like the very first thing we do, we immediately find the correct request. So I'm not going to go into how the vulnerability works. I think it's well written up, but path traversal plus command injection. So the top of the red box has the URL, and the bottom of the red box has the body of the post request with the injection. And depending on how you measure it, so like there are 28 days between us initially finding the incident and the first attempt at a patch, or 15 days between us exactly telling them what the vulnerability was and the patch. But that didn't go very well because subsequently there was like mass exploitation of the vulnerability. So the patch goes live, but there's no auto patching. People are having to manually apply the patch. That takes time. And the attackers for this vulnerability were relatively aggressive, and they seemed to be prepared for this scenario. So as soon as news went public that they were about to lose their kind of way in to various networks, their approach was to exploit everyone and worry about who they had exploited later, and then kind of work on the intrusions afterwards. So yes. So our second case is Palo Alto Networks, and you should see a theme amongst the structure of this. So like all of my best stories, this story begins with an alert. This is just a different alert. So this is a Yara alert for suspicious Python content. And in this case, there's less kind of how did this begin? Because the first device that we're looking at is the Palo Alto Networks device. So this is almost the first thing the attacker did. It's like I should have had the bad luck Brian meme with like has 0 day, gets caught on first command kind of template. We will make a note of that for future editions of this slide. But yeah, rule written in 2021, paid dividends in 2024. We use Yara heavily. We use it against all files that we extract from any PCAP or network data, and that's what's happened in this case. And in fact, so this happened like a morning where Stephen and I were actually at a conference, and then Stephen couldn't attend most of the conference because of it. But the investigation picked up pace really fast. So we had that first alert, and within like hours, there's like multiple other alerts for various other things. The attacker is almost making an effort to make sure we notice. The MS Defender for Identity alert was neat because we don't, like generally those seem to be fairly good. It's worth highlighting things that work. And another thing that was good about this investigation is that following the Avanti investigation, we did have like a thought experiment internally where we thought, hey, what would happen to all of our other customers who have these types of device? What would we be able to do forensics? So as it happened, we had already spoken to Palo Alto Networks about what we would do. And so we already knew the right people. And I also used to work there, which helps. So yeah, we were able to gain root access to the device within kind of the day. So yeah, no ICS VPN device this time, Palo Alto Firewall. And because we were fairly quick, we were able to get loads of information about what they had done, and also we had all the alerts that we'd generated for them downloading all of their tools to the firewall. But kind of, like, I suppose the interesting thing is the very first thing they did is copy the config from the firewall, which has like key data you can use to forge requests in the future, things like that. Second line is trying to delete evidence of the exploitation, which didn't work. No, the exploitation worked, the deleting did not work. And then downloading various kind of web shells and reverse shells. So yeah, they tried to delete evidence, but they didn't understand that evidence would also be in the second folder. There were two places where the same kind of evidence would be written. And so, hey presto, you're on the device, you see this, you think, oh, it's probably in an endpoint relating to device telemetry, which is the endpoint that was vulnerable. It's worth pointing out again that memory analysis makes things very easy, especially on these devices actually. The hard part is getting a profile, but if you have the profile, then generally there's not too much happening on these devices. And so the attacker's activity sticks out like a sore thumb, whereas on like a typical Windows endpoint that a user is using, if they have like 25 applications open, there's a lot of processes, and it's hard to discern what's what sometimes. But yeah, in this case, it's open and shut in terms of the things in the red box are malware, and they're the first thing you see when you open Volcano. It was like annoyingly fast in some ways because Stephen and I were very busy at the time. We were trying to have drinks with friends, catch up with conference material, But there were 2 days between the discovery of the incident and public disclosure. So Palo Alto were very fast. And because of the way Palo Alto, they have this ability to deploy kind of signatures to the firewalls, which were able to intercept exploit requests for their own device. It's an unusual feature, I suppose. But yeah, as far as we were able to tell, subsequent exploitation was pretty limited to just probably hundreds of devices rather than thousands. So I'm not really in the space of consulting or like giving big advice about these things, but I have some general thoughts about edge devices and things that work in terms of detecting stuff. So this slide is a sales slide, really. This is what we present to people when we're talking about our company, because we're very proud of our track record of finding vulnerabilities. And so these are all vulnerabilities for which we are either credited with discovering the vulnerability, or for which, annoyingly, we knew there was a 0-day, but we couldn't prove it before someone else did. And so we're very proud of that. But if you take away the services that are not on the edge of the network, it looks like this. So you'll see that most of them sit on the edge of the network. So most of the big intrusions we're working are happening on the edge. And then, maybe surprisingly, if you take away the products that are not security products, you're still left with half of the field, which is a little concerning. So yeah, I think there's a lot of, it's kind of a well-documented thing that people have spoken about for the past 12 to 18 months, but there's a lot of technical debt in these products that is hard to overcome. And at least kind of a question of like, who watches the watchman kind of question, who watches the edge security device. These things are exposed to the internet. They often, well, there's almost always no way of monitoring what's going on them. So when a vulnerability does become available, there isn't really an avenue to alert on it until something happens elsewhere in your network. Nearly all of the vendors of these devices have some version of the integrity checker tool I described, but the thing is that the device itself is compromised, and so the attacker knows that that tool exists and will try to either subvert it or disable it. And so generally, it's problematic. In terms of detection and response, in both cases, PCAT was incredibly useful. It's maybe less popular than it was at one point, but having network data for these incidents made it really easy for us to discover which machines were infected, like what tools the attacker used, various things like that. Once we identify in any case, so like, but for various incidents we've discovered over the years, we identify these kind of crown jewel systems and we put in kind of traps so that in the first case, it was the Exchange server where we have quite a lot of custom rules around that specific server. And unexpected protocols is like one example of the type of trap you can set for those devices. And then also, while attackers often take great care about ingress to the network, they take a lot less care about file transfer within it. So monitoring files transferred via SMB within a network is very helpful. More in the first case than the second, but the attackers were fairly good at not using malware, so the only malware they used was on the edge device. All the internal stuff, a bit like Stephen's talk, was kind of just like Windows functionality, RDP, stolen credentials. And really, like a lot of my friends like in the industry will be like, oh, you guys discover quite a lot of things. How do you do it? I would say the number one thing that leads us, or one of the main things, is that we're able to do forensics so fast. So we go from alert to investigation within the same day. And we're able to do that partly because of the setup, but also because we have customers who kind of understand the problem and know and trust us, and that's really helpful. And so building those relationships, either if you're like a security team and you have to integrate with an IT team, building that relationship there is important, or if you're a service provider and you've got customers, then making sure they know and trust you is important. And that is all I have to say about that. Thank you very much.